This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on Taylor polynomials. Let's define our term. A Taylor polynomial of order n centered at C looks like the following. A0 plus A1 times x minus c plus A2 times x minus c squared plus A3 times x minus c cubed, ending at a sub n times x minus c to the nth power. Now, let's look at a special case where we have an order 5 Taylor polynomial centered at 0. That will be a sub 0 plus a sub 1 times x minus 0 plus a sub 2 times x minus 0 squared plus a sub 3 times x minus 0 cubed plus a sub 4 x minus 0 to the 4th plus a sub 5 x minus 0 to the 5th. Ending at 5 since it's order 5. Now, of course, we can write this in a slightly simpler fashion. X minus 0 is just x. So that's x, that's x, that's x, that's x. And it looks like this. In the event we have a Taylor polynomial centered at 0, we can also call it a Maclaurin polynomial. So every Maclaurin polynomial is a Taylor polynomial that's centered at 0. So if you see that term, you'll know what it means. We want a Taylor polynomial, Taylor series of order 5. Taylor polynomial is a better word. Of order 5 centered at 0 for the following function. So I'm giving you the values. F of 0 is 1. F prime of 0 is 3. F double prime of 0 is 8. F triple prime of 0 is negative 30. Fourth derivative of 0 is 96. Fifth derivative of 0 is negative 360. We want a fifth order Taylor polynomial centered at 0 for that function. And it looks like this, and our goal becomes to solve for A0, A1, A2, A3, A4, and A5. If we can find those coefficients, we have established our fifth order Taylor polynomial. Now, if we plug 0 in, A1 times 0 is 0, A2 times 0 squared is 0, A3 times 0 cubed is 0, A4 times 0 to the 4th is 0, A5 times 0 to the 5th is 0. All that's left is a sub 0. So P5 of 0 is a sub 0. F of 0 is 1. And the strategy requires the polynomial and the function to agree at all of the derivatives as well as at the original function. So I want P5 of 0 to be F of 0. If that's the case, A1 has to be 0. Next up, we'll take our derivative of P of x. So P prime of x, derivative of A0 is 0. Derivative of A1x is A1. Derivative of A2 times x squared would be A2 times 2x, or 2A2x. The derivative of A3 times x cubed would be A3 times 3x squared, or 3A3x squared. Derivative here, A4 times 4x cubed, 4A4x cubed. Derivative here, A5 times 5x to the 4th, 5A5x to the 4th. So, if we're plugging in 0 for x here, this is 0, this is 0, this is 0, this is 0. All that's left is A1. So P prime of 0 is A1. F prime of 0 is 3. And again, we want P prime of 0 to equal F prime of 0. If that's the case, A1 has to equal 3. So we've solved for A0 and A1. 4 more for us to do. So our next goal is to get the second derivative. You'll notice we have the first derivative here. The derivative of A1 will be 0. The derivative of 2A2x is 2A2. The derivative of this will be 6A3x. Derivative here, 12A4x squared, 20A5x cubed. And if we plug 0 in here, what do we get? 0, 0, 0. P double prime of 0 would be 2A2. And F double prime of 0 up here is 8. So if 2A2 is 8, dividing both sides by 2, we get A2 is 4. We still need to find A3, A4, and A5. I will have to take the third derivative. So the derivative of 2A2 is 0. Derivative of 6A3x is 6A3. Derivative of 12A4x squared would be 24A4x. And derivative of 20A5x cubed would be 60A5x squared. So knowing this, plugging in 0 for x, this piece is 0, this piece is 0. P triple prime of 0 is just 6A3. f triple prime of 0 is negative 30. So if 6a3 is negative 30, dividing both sides by 6, a3 is negative 5. Next, we need the fourth derivative. So let's take the derivative of this piece. Derivative of a constant is 0. Derivative of 24a4x is 24a4. Derivative of 60a5x squared is 120a5x. Now plugging in 0 into the fourth derivative, 120a5 times 0 is just 0. The fourth derivative at 0 will be 24a4. The fourth derivative at 0 up here is 96. We want the fourth derivative at 0 of the polynomial to be the same as the fourth derivative at 0 for the function. So 24a4 has to equal 96. Dividing both sides by 4, we get a sub 4 is 4. And our last derivative, the fifth derivative, derivative of 20a4 is 0. Derivative of 120 a sub 5 times x is 120 a sub 5. So the fifth derivative of that polynomial is going to be 120a5. So the fifth derivative at 0 is also 120a5. The fifth derivative of the 0 of the function is negative 360. So therefore we need 120 a sub 5 to equal negative 360 because we want these derivatives to match. Of course that should be p5. And that's fixed. So the fifth derivative of p at 0 is 120a5. The fifth derivative of f at 0 is negative 360. 120a5 is negative 360. Dividing both sides by 120, we get a5 is negative 3. So we have a3, a4, and a5. On the earlier slide, we had a0, a1, and a2. Let's put all those together. There are the 6 coefficients we need. We want a fifth order Taylor polynomial of order 5 centered at 0, which looks like this. Then all I have to do is plug those numbers in for the coefficients. So 1 plus 3x plus 4x squared plus negative 5x cubed plus 4x to the fourth plus negative 3x to the fifth. And that gives me my fifth order Taylor polynomial centered at 0 for that function. Now I can use this to answer an interesting question, namely, this is centered at 0, so I should be able to approximate the value for f of 1/2. 1/2 is pretty close to 0. You would think you might get a reasonable approximation since this Taylor polynomial is centered at 0. So to get f of 1/2, we're going to plug 1/2 in for each of the x's. So p5 of 1/2 will be 1 plus 3 times a half plus 4 times a half squared minus 5 times a half cubed plus 4 times a half to the fourth minus 3 times a half to the fifth. And what will that be? That's, of course, a quarter, an eighth, a 16th, a 32nd. So 3 times a half is 3/2, 4 times a quarter is 1, 5 times an eighth is 5/8, 4 times a 16th is a quarter, 3 times a 32nd, negative 3 32nds. And then just adding up those fractions, we get 97 32nds. So you can use a Taylor polynomial to approximate values of the function near where it's centered. That's one of our advantages. Okay, our next question will be to find a Taylor polynomial of order 4 centered at 1. For this function, f of x is the square root of x. So in the last problem I told you f of 0, f prime of 0, f double prime of 0, etc. I'm not giving you those derivatives. We're going to have to compute them. It's centered at 1, so we're going to see a0 plus a1 times x minus 1 plus a2 times x minus 1 squared plus a3 times x minus 1 cubed plus a4 times x minus 1 to the fourth. So there is our Taylor polynomial of order 4 centered at c. If we're centered at 1, c becomes 1. And then our goal, as in the first example, is to solve for a0, a1, a2, a3, and a4. And let's go do that. So we're starting with our function f of x is the square root of x. I need to find f of 1. Well, f of 1 is the square root of 1, which of course is just 1. Next, I'm going to need f prime of 1, but to get that, I've got to take the derivative of x to the 1/2. So f prime of x would be 1/2 x to the negative 1/2 using the power rule. X to the negative 1/2 means 1 over x to the 1/2, or 1 over root x. So f prime of 1 would be 1 over 2 times the square root of 1, or 1/2. So I have f of 1, and I have f prime of 1. If I want the second derivative, that'll be 1/2 times negative 1/2 x to the negative 1/2 minus 1. So 1/2 times negative 1/2 x to the negative 3/2. So 1/2 times negative 1/2, negative 1/4, x to the negative 3/2, or negative 1/4 times 1 over x to the 3/2. Well, we're using 1, so f double prime of 1 is negative 1/4 times 1 over 1 to the 3/2. We just get negative 1/4. 1 to any power, of course, is just going to be 1. To get the third derivative, negative 1/4 times negative 3/2, that would be what, 3/8, times x to the negative 3/2 minus 1, negative 5/2. Then we're going to plug in our value of 1 here, so 3/8 times 1 over 1 to the 5/2. 1 to the 5/2 is 1, and we just get 3/8 for f triple prime of 1. And I believe we're doing fourth order. If that's the case, we've got to go ahead and do one more derivative. So I have 3/8 here, x to the negative 5/2. So the next derivative will be 3/2 times negative 5/2 times x to the negative 7/2. Because if you decrease negative 5/2 by 1, you're at x to the negative 7/2. So negative 15/16 times 1 over x to the 7/2. Plugging in 1 for x, we get negative 15/16 times 1, negative 15/16. So we have f of 1, f prime of 1, f double prime of 1, f triple prime of 1, f quadruple prime of 1. We need all of those pieces of information to find our coefficients of our Taylor polynomial. So here's all the information we've constructed on the previous slides. Now we have to remember what our polynomial is going to look like. It looks like this. If we plug 1 in, this becomes 0 because 1 minus 1 is 0. This becomes 0, this becomes 0, and this becomes 0. So p of 1 will just leave a sub 0. F of 1 is 1. We want these to match. So a sub 0 will equal 1. Next up is our derivative. The derivative of a constant is 0. The derivative of a1 times x minus 1 is just a1. The derivative of x minus 1 squared is 2 times x minus 1 to the first times the derivative of the inside, which is just 1. So I get 2a2 times x minus 1. The derivative of this piece will be 3a3 x minus 1 squared times the derivative of the inside, which is just 1. The derivative of this piece, 4a4 times x minus 1 cubed. As I plug in 1, this is 0, this is 0, and this is 0. All that's left is a1. So p prime of 1 is a1. F prime of 1 is a half. We want these to equal, so a1 will equal a half. Second derivative here will be 2a2. Derivative here, 6a3 x minus 1 to the first. Derivative here, 12a4 x minus 1 squared. Plugging in 1, this is 0. Plugging in 1, this is 0. So p double prime of 1 is just 2a2. But f double prime of 1 is negative 1/4. If that's the case, I want these to be equal, so 2a2 is negative 1/4. Dividing both sides by 2, a2 is negative 1/8. The next derivative, this gets tedious, yes. The next derivative, the derivative of 2a2 is 0. The derivative of this piece will be 6a3. The derivative of this piece will be 24 a sub 4 times x minus 1. Plugging in 1 here, that'll be 0. We'll just be left with 6a3. So p triple prime of 1 will be 6a3. F triple prime of 1 is 3/8. Knowing that, then 6a3 has to equal 3/8. So a3 is 3/8 times a sixth. Notice 3 goes into 6 twice. That cancels. 8 times 2 is 16. So we get a3 is 1/16. And we have one more coefficient to get. The derivative of 6a3 is 0. The derivative of this piece will be 24a4. So the fourth derivative of x is 24a4. Of course, the fourth derivative of 1 is also 24a4. The fourth derivative of f at 1 is negative 15/16. If that's the case, then 24a4 should be negative 15/16. Multiply both sides by 1/24. I think we lose a 3 here. So 3 goes into negative 15 negative 5 times, 3 goes into 24 8 times. We get negative 5 over 128. So now we have all of our coefficients, a0, a1, a2, a3, and a4. We will use them to construct our fourth order Taylor polynomial. So plugging in those coefficients, we will finish with P4 of x is a0, 1, plus a1 plus a half, x minus 1, plus negative an eighth, x minus 1 squared, plus a 16th of x minus 1 cubed, minus 5 128ths times x minus 1 to the fourth. But remember what this was for. This polynomial is supposed to approximate the square root of x near 1. So I want to look at the graph of this polynomial, and I want to look at the graph of the square root of x and see just how close they are. So the square root of x is this graph in red. You can look at our range. X is going from 0 to 3.5, y from 0 to about 1.5. Whereas the polynomial we just constructed is in blue. And you'll notice that the square roots domain starts at 0. We cannot take square roots of negative numbers for real valued functions. But the polynomial is okay with that. But you can see near 1, these two functions are very, very similar. So if we wanted to, we could approximate the square root of 1.5 using our polynomial, or the square root of a half using our polynomial. Of course, recognize that polynomials are easy to evaluate limits, easy to evaluate derivatives, easy to evaluate integrals. So that's one reason for us to compute Taylor polynomials for these kinds of functions. And that will conclude this lesson.